Trust you too. Yes. Alright. So we're starting class today with the periodic table. Anybody able to tell me why we have the periodic table here? What does this have to... Yes.
Oh, so like you have the carbon atom, carbon 12, and there's different isotopes. Oh, yes. So the periodic table is given to you in atomic mass units, and it's relative, like how big an atom is relative to the carbon atom. So that's why you have like the carbon atom was designated 12.011 for its atomic mass units.
But why do I care about this in Calc 3?
Oh, okay.
Why tables? Yeah, there's a lot of reasons. There's a lot of stuff. Yep. Nope. Nope. Any other reasons why I care about this?
Because of its organization.
Because of its organization. It's an example of a series of things you sum. It's a sequence, right? This is one of the greatest sequences of all time. So this was inspired by one of my Calc 3 students last year who liked the class overall, but did not like the units on sequences and series. He just felt unmotivated, and he was a chemist. And so even though he's not here now, I will tell him to watch this video, and so hopefully, a year later, he will now look back fondly on sequences and series. This was one of the greatest scavenger hunts of all time. What do I mean by that? Who knows their chemistry?
Well, you started off with the elements that you could see, but like the transition state metals are not ones that you readily find all the time, and you a lot of chemists found them time scattering through the last two rows, which are very hard to isolate because they're so radioactive.
Yeah.
It became, I think, apparent fairly quickly that there was an element for each atomic number, but then they had to find them.
Right, and so by organizing things like this, it actually helped chemists and others in their search for missing elements. And in fact, it told them there's some gaps in your sequences, you're missing certain terms. And so to me, this is a great example of the powers of sequences and series. Now, I'm not going to give you an arbitrary problem. Let's sum the first 4 rows and see what the total, no, that's not what you're supposed to be doing with the periodic table. But it is a great example of sequences and series. Right? We may be seeing it all day because the cloud doesn't want to go. Okay. So what we're going to do for the rest of today is do the comparison test, and then some other simple consequences. So you should make sure you email me for extra credit because it's going to be hard video work today.
Okay.
Right. So the comparison test. So here's the framework. Let an goes from 1 to infinity, similarly bn and cn be sequences of non-negative numbers. And let's assume the sum n goes from 1 to infinity of Cn equals plus infinity, so it diverges. And the sum n goes from 1 to infinity of Bn is less than infinity, so it converges. The comparison test allows us to occasionally deduce information about the sums of the sequence an by comparing it to sums that we know. So the problem is right now we do not know that many series that converge or diverge. Our list is very sparse. We're going to try to add more things to that today. So for example, let's see what it says. So 1. If 0 is less equal to an is less equal to bn, then what can we deduce about the sum of an? Yes?
That it's less than the sum of bn?
So it's less than the sum of bn, and in particular it, less than infinity, it converges. And you're absolutely right, we know more than just that it converges, we have an idea of how big it can be. It can't be larger than the sum of bn. And this makes sense. If term by term I have a sequence of non-negative numbers that are always less than or equal to bn, and the sum of bn is finite, then the sum of an should be finite. It's very important that my numbers an are non-negative. Otherwise, what could happen is, well, if they were negative, I could be going off to minus infinity. since they're non-negative, every time I add a new term, I can't get larger. I'm sorry, I can't get smaller. I can only stay the same or get larger. And I can never get above this height. So my sum will have to converge. Okay? So this is one comparison. How do you think I should compare AN to CN and get something useful? Okay, good. So if 0 less than equal to Cn less than equal to An, then what do we deduce about the sum of An? It diverges. So term by term, I'm larger than something that diverges, therefore I must diverge.
But what does it mean for AN to be greater than infinity?
No, I'm not saying the CNs themselves are infinity. I'm saying the sum of the CNs is infinity. The sum of the CNs diverge.
Okay.
So the individual CNs are going to be finite numbers. But their sum will be infinity. Their sum will diverge. So right now, we only know 2 divergent series. Well, we know infinitely many, but they're, all but one of them are of the same functional form. Well, we have some other comparisons we could do. We compared AN when AN was less than equal to BN. We compared AN when it was greater than equal to CN. What's another comparison I could do? I've got other things I could do. If 0... So give me a comparison I haven't done yet.
BN and CN.
Well, BN and CN I don't really care about because they're fixed things that are known.
AN times CN?
AN and CN. So if I have 0 is less than equal to AN is less than equal to CN, then what can I deduce? Sorry?
Well, you can't automatically believe that it doesn't diverge because it's still one version.
So I can deduce
It's
nothing.
also infinity?
Well,
When it's
Nothing.
I can deduce nothing. I have nothing here. This is the useless comparison. So I know my sum is at most plus infinity. Wow, that's really helpful. It's like telling you there'll be questions on the final. I hope I haven't given away too much of what's going to come. Or telling you that your score will be greater than 0 and less than 100%. Actually, with the way I do things, you could actually have more than 100% on my final. So, okay, that's a little bit useful information. But if I tell you the sum is less than plus infinity, I have provided no useful information. So, for example, I could take 1 over n and 1 over 2 to the n are less than or equal to 2 over n. This sum diverges, this sum converges, this sum diverges. This gives me no useful information. We have one last possible comparison. If 0 is less than or equal to bn less than or equal to an, then nothing! Right? We have nothing useful in this case. All I know is my sum is greater than or equal to some finite number. Well, if I'm trying to figure out whether or not my sum converges or diverges, knowing that it's greater than a finite number is not enough to help me. So for example, 1 over 2, let's do this. 1 over 3 to the n converges. And this is less than or equal to 1 over 2 to the n and 1 over n. So here again, I have something that converges, and here again, I have something that diverges. Okay? So in the comparison test, there are 2 comparisons that are useful. If you think your sum converges, compare it to something that converges. So, guidelines. If think the sum n goes from 1 to infinity of an converges, look for a bn such that an is less than or equal to bn and the sum of bn converges. if you think the sum n goes from 1 to infinity of an diverges, look for a Cn such that Cn is less than or equal to an, and the sum n goes from 1 to infinity of Cn diverges. This is how you should use the comparison test. The comparison test is the hardest of the tests to use. Okay? You need to know what to compare it to. Alright, well, if we're going to use the comparison test, we need examples of series that converge and diverge. So let's make a little table. How many of you have seen tables of integrals? If you haven't, I've got some big monster tables in my office, and, over 1,000 pages, just integrals. Okay? Now, in the 21st century with Mathematica and online resources, these are not quite as important, but sometimes it's not clear what change of variable you need to make to reduce your integral to a version that's known. So as an aside, somebody gave me a while ago, I think, the integral of 1 over 1 plus x to the 4th dx. And the trick was to write this, I think this was the integral. And the trick was to make the substitution u equals x squared. And then this integral was essentially the same as the integral of du over 1 plus u squared, and now I can give it an arctangent. This is a factor of 2, but a lot of times table of integrals don't have things in the form you want. And that makes them a little bit hard to use. Question?
Just out of curiosity, how do they organize those thousands of pages of integrals?
They organize them by the types of functions you're integrating. Exponential functions times polynomial functions. Trig functions times exponential. They organize it like that to try to make it easy to look through. If you haven't seen a table of integrals, it's worth looking at once in your life. Alright, can somebody give me an example of a series that converges? 1 over n. Does that converge? The individual terms converge to 0. The sequence is converging to 0.
1 over n squared.
So what about the sum of 1 over n? So what do we know about the sum of 1 over n?
It diverges.
Yeah.
It diverges. So that goes on our list of diverges. 1 over n squared was suggested. What is the sum of 1 over n squared? Who remembers?
Tends to 0.
I squared
Pi squared over 6. Can you prove it? Can you prove the sum of 1 over n squared converges? Do you trust me? If you really trust me, you can put 1 over n squared over here, but we have not proven that yet, so I would not put 1 over n squared down yet.
Wait, you don't trust yourself?
No. It's one of the reasons I'm so successful. I do not trust myself. What is an example, and this is being documented, I know.
1 over 2 to the n.
1 over 2 to the n. Do it a little bit more general than 1 over 2 to the n.
1 over 8 to the n?
Sorry?
1 over 8 to the n?
Okay, what's true about a?
A is between 0 and 1?
If a is between 0 and 1, if a is 1 half, then 1 over a to the n becomes 2 to the n.
A is greater than 1?
A is greater than 1. So I'm going to write a more standard r to the n if the absolute value of r is less than 1. So our geometric series. That's an example of something that converges. Well, as soon as I put this here, there should be a corresponding thing now on the divergent side.
R to the n, R is greater than 1?
R to the n, where now r is greater than 1. That's it. That's all we know. So when we're trying to do the comparison test, we don't have that many things to compare to. Now, we have infinitely many choices of r, great, but, alright. So for example, let's take 1 over n squared. What can we compare 1 over n squared to? If you look at what we have on our list, what can we compare it to? 1 over n. And which way does the comparison go? Goes this way, useless. Right? Question? Yes?
We have to compare it to our one convergent series.
Right, but unfortunately we have no good way to do the comparison.
Oh, because it's not smaller.
And so the only thing we know how to compare 1 over n to, 1 over n squared to is 1 over n, and the comparison goes the wrong way. What about 1 over square root of n, written in a highly suggestive manner? What should we compare 1 over square root of n to?
1 over n as well.
1 over n. And so it diverges. So we can at least add something else to our list. And in fact, we could do a little bit more. We could do 1 over n to the p, where p is greater than or equal to 1. That will also diverge.
Do you mean less than or equal to 1?
Ah, sorry, thank you. Because we put it down in the denominator. So 1 over n to the p, where p is less than or equal to 1, will diverge. So in fact, we can expand our list a little bit to 1 over n to the p less than or equal to 1. This is still a pretty crappy list. Right? If we're going to use the comparison test, we need to know a lot more. We want things like 1 over n squared. Or maybe things like e to the x, something like that. Well, right now, we only have these 3 things. And really, these 2 are the same. Okay? So what I want to do now is I want to expand our list of sequences and series that we understand. And I want to just go through a sequence of examples. And in the end, we will go through an example that's, I think, worse than anything on the homework today. The hardest part of this is not going to be the calculus. It's going to be the algebra. So I'm a little hesitant to tell the story because it's being recorded, but I think I legally am allowed to tell it. Years ago, I was teaching a class on differential equations. And I asked the students, how many of you want to see a quick review of linear algebra? I need some stuff about 2 by 2 matrices. Silence. Does anybody want to see? No, nobody. So everybody's comfortable with 2 by 2 matrices. Alright, just out of curiosity, we're going to use our clickers now. Press 1 if you want a review of linear algebra. Press 2 if you don't. Anybody want to guess what percent it was?
100%.
Not 100%. Not that bad.
80?
Not that bad.
60?
Not that, oh, okay. Now I guess it's not that bad. Either 43 or 47%, I can't forget what. But essentially, 1 out of every 2 students wanted to see a linear algebra review, but did not feel comfortable saying so. If you are sitting anywhere except at the extremes, almost surely somebody next to you would want to hear a question you would have about these sequences or series, about the algebra. The hardest part about this unit is not the calculus. It is the algebra. It is being comfortable with these basic functions. So if anything doesn't look clear, and again, you've already seen me do one algebra mistake. I wish I could say that was deliberate, but I'd be lying. Ask questions. Almost surely the people around you will be grateful. They won't let you know that. Unless you look really closely at their faces. So please ask questions if any of the algebra seems unclear. Right. So I'm going to erase our list because I think we understand our list. That's been internalized. Yes?
Could we add n factorial to the divergent list?
We could, and to the divergent list.
Because it gets larger and larger, so...
Well, if it's getting larger, just the sum of n factorial. Yes, we
Yeah.
could add that to the list.
Okay.
Yes.
But it wouldn't be...
That wouldn't be the useful one. We want 1 over n factorial,
Okay.
which converges, but we don't know yet why.
We could do all of the e to the x factorials.
But why does that
No, not the
converge?
e to the x factorials and e to the x series.
Right. But we need to know that n factorial converges. We need some control over the growth rate of n factorial. If there's time today, I'll talk and give you a quick proof of why that converges. But right now, we technically don't know that. We need to somehow fix that. So let's do the following example. Let's let an be 1 over 2 to the n plus n. And let's look at the sum. N goes from 1 to infinity of 1 over 2 to the n plus n. What do you think? Converges or diverges? So I think I heard something from this part of the
Converges.
Why converges?
Because it probably grows, the denominator will be growing way faster than that of 1 over n. But it's just like a guess.
Okay. So I could compare this to 1 over n. Which way would it be compared to 1 over n? Larger or smaller?
Smaller.
Smaller. So 1 over 2 to the n plus n is less than or equal to 1 over n. Useless. Right? It doesn't help me to be smaller term by term than something that diverges. Okay? So that's not going to be useful. What could I try to do instead? Yes?
If we compare it to 1 over n squared,
We don't know 1 over n squared converges.
Compared to 1 over 2n.
Yeah, compared to 1 over 2 to the n. 1 over 2 to the n plus n is less than or equal to 1 over 2 to the n. This sum converges. Therefore, this sum converges. The way to view this is when n is large, what does the denominator look like? If n is huge.
Oh.
It does look like 0, but let's do a refined 0. So if n is 10,000, what is the denominator for all practical purposes? What number does the denominator look like if n equals 10,000? It's really large. Approximately what really large number is it? A of 10,000 is approximately 1 over
2 to the 10,000.
2 to the 10,000. Who wants to have a really good day? Alright, Joel. I am going to put $2 to the $10,000 in your bank account today. But you have to buy a lot of munchkins for all the Williams students, and you're going to have to spend $10,000 buying munchkins. Totally fine. Okay? The munchkin view of mathematics. Okay? So, if I give you $2 to the $10,000, you don't really care about a $10,000 one way or the other. Technically, in this problem, I'd also be giving you $10,000 as well. And, well, you might be happy to get an additional $10,000. At this point, you really don't care. You just got 2 to the 10,000. Okay? When you have really large numbers like this, you can basically say, screw them. And it's essentially just, 1 over 2 to the n. Okay. Any questions about this? We're going to start to slowly tweak this problem. Yes?
do we have like a largest convergent series?
That's a great question, and one of the classic books in mathematics is called Baby Rudin. That's the actual name of the book in the mathematics community. The official title is Principles of Mathematical Analysis. And it has a wonderful section where it talks about trying to have a dividing line between converging and diverging series. And in some sense, you can get as close as you want. You can flip-flop between converging and diverging with log games.
So, if you had 1 to the 2n minus n in the bottom...
We're going to get to that later. So you see the punchline. So we're gonna wait on that one. Right now I'm going to modify this. Is everybody ready for the modification? Okay. And you also have a glimpse as to the future. After that we're going to do a minus sign. We'll do maybe 1 or 2. Converge or diverge. I'm replacing the 2's with 4's. Why?
Because it's even smaller.
It's even smaller than before, right? I could compare this to 1 over 2 to the n. Or I could compare it to 1 over 2 to the n plus n, which we just did a moment ago. Which would you rather compare to? I'm sorry?
Say it again.
Which would you rather compare this to? 1 over 2 to the n or 1 over 2 to the n plus n? 1 over 2 to the n. It's the standard representative example of a grid geometric series. The other one is a tweak. It's not on the standard tables. You have to write a little bit more math. Go for the easiest comparison. So everybody agrees this converges. Compare to 1 over 2 to the n, and you get 1 over 4 to the n plus n is less than equal to 1 over 2 to the n. Okay, everybody's comfortable with this. Alright, it's time for another tweak. Okay? So what I'm going to do now is, we know that this converges. If I just had the n in the denominator, it would diverge. If I didn't have the n, it would converge. So the denominator is growing, and it's growing really, really fast. Let's help out the divergence case. And let's make the numerator large. And if I make the numerator large, I'm going to have more of a chance of diverging. So I will make the numerator 2 to the n. Is this enough now to push it into divergence? Why not?
Because, oh no, never mind. No, that wouldn't be good.
If you divide the denominator and numerator and denominator by 2 to the n.
Okay, so one thing is I could pull in the 2 to the n of the denominator and get 1 over 2 to the n plus n over 2 to the n. Another thing is I could just do a direct comparison. What should I compare? I'll put this in the middle. Do I want to find something larger than this or something smaller than this? Larger. I think it converges. So I think it converges. I want to find something larger. What's the natural candidate?
1 over 2.
Okay. What's the natural candidate said in the natural way? The natural way is not to say 1 over 2 to the n.
2 to the n over 4.
2 to the n over 4 to the n. So the natural comparison is to basically say, ignore this plus n. And then this is the same as 1/2 to the n. So this sum converges, this sum converges. Okay? So let's be a little explicit. Let's take 1 over 2 to the n plus n. Let's go back a little bit in time, and let's take 1 over 2 to the n. Are these both visible by the camera, or is this too low?
It's still visible.
Okay. So the first few terms of 1 over 2 to the n is 1, 1/2, 1/4, 1/8, 1/16, 1/32. If I go over here, the first term when n equals 0 is 1 as well. Then when n equals 1, I get 2 plus 1 is 1/3. Then when n is 2, I get 1/4 plus 2 is 1/6. 1/11. When n is 4, 1/20th. 1/37th. Dot, dot, dot. In the beginning, you can see there's a sizable difference between these terms. But in the limit, as we go along, and I got bored, so I stopped after n equals 5, you can see that these terms are really approximately the same. These ones are just a little bit smaller. So the effect of this plus n is really being washed away. And this is leading up to what we're going to do now, and this was suggested earlier. Well, what if we made this 4n minus n? And that's why I wanted to just quickly write this down. So now, is everybody ready for the 4n minus n? Okay. I'm going to change what do you think now? Converge or diverge?
Converge.
Converge. And again, if you want, as was suggested, put the 2 to the n down below, you'll have 1 divided by 2 to the n minus n over 2 to the n. Now, the n over 2 to the n is very small. Okay. So let's try to think what we should compare it to. So should I compare it to something larger or smaller? Larger. So I want to compare, so I have 2 to the n over 4 to the n minus n. What's a good comparison for the denominator?
4 to the n.
I'm sorry?
4 to the n.
Well, if I do 4 to the n, does the comparison go this way? No. So if I do it this way, unfortunately, the comparison now goes like this. And so we lose.
3 to the n?
3 to the n. Excellent. Why should we do 3 to the n? So we're basically comparing it to 2/3 to the n. But why should I use a 3 down here for 4 to the n minus n?
I'm just gonna make it greater.
Yeah, so 4 to the n minus n turns out to always be less than or equal to 3 to the n. So here's 4 to the n minus n, here's 3 to the n. When n equals 0, we get 4 to the 0 minus 0 That's 1, that's 1. When n equals 1, we get 4 minus 1 is 3, 3. When n equals 2, we get 16 minus 2 is 14, 9. I'll do one more. When n equals 3, we get 64 minus 3 is 61, 27. We can see the 4 to the n minus n is growing much faster than 3 to the n. So if I replace the 4 to the n minus 1 with 3 to the n, I'm making my denominator significantly smaller. Thus I'm making the fraction sufficiently larger, significantly larger. Okay? This is the time now to do an expansion of the comparison test. So the comparison test as written is correct, but there's a more useful version. And to get the more useful version, I'm going to change the problem again. I'm going to put a 2 here. Do you think it really changes things by putting a 2 there? No. Alright, let's see what happens. Let's explore the consequences. So now, when n equals 0, what do I get?
Are you missing an n?
Oh, sorry, I am missing an n. Thank you. Put a question mark here. So when n equals 0, now what do I get? I still get 1. When n equals 1, I get 4 minus 2 is 2. Oh dear. 2 is less than 3. I'm now comparing it to something that's going to be smaller. What about the next term? When n equals 3, what do I get? I'm sorry, when n equals 2, what do I get? I get 16 minus 4, 12. Alright, that's good, that's greater than 9. When n equals 3, I get 64 minus 6, 58. And in fact, from this point onward, we'll be okay. So we're okay except at one point. You know, when n equals 1, the comparison breaks down. How bad is this?
Doesn't that not matter though, because we're summing the whole series or not?
So we're summing the whole series. So whether or not something converges or diverges is independent of one term. It's independent of 10 terms, 1,000 terms. Any finite number of terms I can change. Okay? Yes?
Does it work also if you can like let's say all the terms are larger, but like if you shifted a different series like this way, you could get them to match out.
You can play games like that. You might have to like re-index the series, you know, just because of the way we're phrasing things. But the idea is if we go back to the comparison test, what we can do is for all n sufficiently large, so can feel finitely often. So we can throw away finitely many terms of the two series. Will that affect the value of the series? The value of the series. So there's two questions. Does the series converge or diverge? And two, what does it converge or diverge to? So if I change everybody's third midterm to a 0, will that affect your midterm average? Well, but for some of you, some of you did better on the third midterm. Let's do a standard math class where you are stuck with every score you get. Okay? If I replace one of your exams with a 0 in a standard math class, where you don't need a PhD to follow the grading, will that affect your average? Yes. Will it affect whether or not the sum of your scores converges? Okay. I can change finitely many terms without changing whether or not things converge or diverge. So over here, if I want to do this comparison, I would be okay, and I can write this as less than or equal to, as long as I write n is greater than or equal to 2. And if I write n is greater than or equal to 2, then I'm okay.
So then, could you just compare like the infinity term of two series?
No, you can't do just the infinity. You have to you can compare all terms from some point onward. So I can throw away the first 55 quadrillion terms if I want, and it's not going to change things. Okay. So imagine I have 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 16th plus dot dot dot. Anybody remember what that sum equals?
2.
2. What if I give you 1 plus 1 half plus 1 over 2014 plus 1 eighth plus 1 16th? So I just changed this term, and I changed nothing else. Does the new sum converge?
Yeah.
Yes. What does it converge to?
Almost 2.
Almost 2. It converges to 2.
Minus 1/4 plus 1 over
Yes.
2014.
That's the best way to write what it is. I've changed the value of the sum in a very finite computable way. I do not change whether or not the sum converges or diverges. And in fact, I could have changed finitely many numbers. I could have changed the first 2014 terms of the series to be 2014. Not even 1 over 2014, just 2014. And that's not going to affect whether or not the sum converges. Will it affect what it converges to? Yes. If I look at all the bank deposits you've made in the last year, and I change it by adding a 0 as the last digit, will that affect the sum in your bank account?
Yes.
Yes. Does it affect whether or not the sum in your bank account converges or diverges? No. Did you have a question?
You can only throw out the first few terms, not everything.
You can only throw away finitely many terms. So finitely many terms can piss you off and be discarded, but you have to keep everything from some point onward.
So does that mean that you can never change a finite sum into an infinite sum?
You can never do finitely many things to make a finite sum infinite. Yes. I can make a finite sum infinite by doing infinitely many things. Not surprising. Just change every term to 1. And if I do that infinitely often, the sum will diverge. But I can only make it diverge if I do infinitely many things. Other questions about this? So now we can begin to get a lot more with the comparison test. The comparison test is the hardest one to use because you need to know what to compare to. This is where it's a bit of an art. But it's also one of the easiest. All you have to do is just find something that term by term is larger, or is just larger from some point onward. If it converges, your thing converges. Find something that's smaller term by term. If that thing diverges, then you diverge. It's can you find those examples? And this is why we need to have as many examples as possible. Okay. So what I want to do now is I want to spend the last few minutes doing a very simple test for convergence divergence. Okay. Fact. So we have a sequence A1, A2, A3, A4, dot, dot, dot. We form the partial sums S1, S2, S3, dot, 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 where Sn is A1 plus An. So again, this is the language. So really, whenever I talk about a series, I'm talking about whether or not the corresponding sequence of partial sums converges or diverges. There's really no difference between talking about sequences and talking about series. Okay, I can go back and forth between the two. Imagine the partial sums converge to some finite number s. So, i.e., the limit as n goes to infinity of Sn, which is the sum n goes from 1 to infinity of An, equals some finite number. What can you tell me about the individual Ans?
Diverge.
So, why diverge?
Because they just keep growing to infinity, like, individually.
Well, I'm saying this, the partial sums converge, so the sum of the ANs converges.
They get smaller and smaller until they eventually reach 0.
They have to be getting to 0. Because if they weren't getting to 0, if they were getting larger, my partial sums would be getting larger. Or if my ANs alternated sign, then my partial sums would be alternating as well. The only way the partial sums can stabilize is if what I'm adding from some point onward is insignificant in the limit. And so what that means is the ANs have to tend to 0. And the limit, as n goes to infinity, of AN equals 0. Okay? So this is a great fact. If a series converges, the terms tend to 0. Okay, so we've got the fact. If a series converges, terms tend to 0. What do you think the flip of this is?
The series diverges, the terms tend to infinity.
That's a little bit more of a flip.
The series converges and its terms tend to not 0. Anything but 0.
No.
If the series diverges, the limit of, or the terms tend to anything greater than 0.
Okay, so a conjecture might be if a series diverges, the terms do not converge to 0. Is this conjecture true or false?
False.
Okay, what disproves it?
So like the harmonic series. would
Harmonic
disprove it.
series.
So it's exactly the opposite.
No, I wouldn't say exactly.
Well, it's like the reverse.
So if I look at 1 over n, in 1 over n, the terms are tending to 0, but the series diverges. So here an goes to 0, but the sum diverges. So this conjecture is false.
You mean the sum converges, right?
No, the sum of 1 over n diverges. So it's possible. Okay, so if the series diverges, the terms do not converge to 0. So here's an example of a series that diverges, but the terms tend to 0. So unfortunately, the terms can tend to 0 if it converges, the terms can tend to 0 if it doesn't converge. What we do have is the following fact.
That's the sum.
If, is something wrong?
No. I don't think it's very clear about it.
1 over n, the sum
of 1 over n diverges. That's the harmonic series.
Okay.
So we proved that last time. That was with the 1/2s. The 1/3 plus 1/4 is at least a half. 1/5 plus 1/6 plus 1/7 plus 1/8 is at least 4/8, which is a half. And when we keep grouping it like that, we see that the sum of 1 over n diverges.
Okay.
So really we only have 2 divergent series right now at our disposal. 1 over n, and tweaks of it, like 1 over square root of n, and then r to the n when r is greater than 1 in absolute value. So the fact is, if an does not converge to 0, then the series diverges. Why? Well, if the series converges, we just showed that anytime the series converges, the terms tend to 0. So if the ANs are not converging to 0, the series has to diverge. Unfortunately, that is all we know.
Well, but doesn't the an converge to 0 in the case of 1 over n?
I'm sorry? Yes, so that's the problem. Just because an converges to 0 does not mean the series converges.
Okay.
If the series converges, the terms tend to 0. If the terms tend to 0, it may or may not converge. If terms tend to 0, might converge.
But the series will definitely diverge if an does not converge
Yes.
to 0.
So if the ANs go off to, do not converge to 0, it has to diverge. So when I give you a series on an exam, what do you think will be true about the ANs?
They will converge to 0.
Almost surely they'll converge to 0. Maybe I'll try to put in one problem where the ANs don't converge to 0. But most of the time the ANs will go to 0. You should look at these as lower order terms, trying to understand what's going on. You have your main term, and then you have your corrections. So think of the infinite sum as the reality. And then you hope that you only need a few terms to get a really good sense of what's going on. That the lower order terms don't matter that much. So over here, once I'm at 1/16, I'm essentially at 2. Anybody know how far away I am from 2? Yes.
Another 16.
Another 16. So I'm off by 1/16. If I went to 1/2 to the 10,000, then I'm missing 2 by 1/2 to the 10,000. Okay. So at that point, I'm essentially at 2. Okay. So the hope is that in these partial sums, if you take enough terms, it's a really good approximation to reality. And then we have some way of controlling this. So remember the bad calc book that I'm reviewing. I'm not going to say which book. It said the ellipse perimeter is pi a plus b. And that's wrong. But you can write it as the answer is pi a plus b plus a1 plus a2 plus a3. And these numbers are rapidly decreasing. And this series actually converges fairly quickly. So if you just take a few terms, you get a pretty good approximation. That's one of the whole goals, is we want to find good approximations to things. Okay, we've got about 2.5 minutes. Any questions on what we've done? So I'll make one comment. This is really something I've been talking to some people in this class about. How many of you have taken any quantum or seen any quantum? Okay, what's one of the most important constants in quantum? Planck's constant. So a lot of times in quantum mechanics, you expand things in terms of h or h bar. Anybody know what h bar is? It's not where it goes through. It's h divided by 2 pi. It turns out to be very convenient to use this normalization. H turns out to be very small relative to the other physical quantities that are in the problem. And so you can often expand things in terms of these power series in h. In the limit as h goes to 0, you recover classical mechanics and quantum mechanics evaporates away. And then you can kind of measure the quantum effect by looking at these terms, by looking at how strong is that h term. That's going to be the main contribution from quantum. So the idea is for a lot of problems you have, you might have some kind of interactions in some kind of chemistry system. And the hope is that things that really matter are the ones that are pretty close. Okay. I want to end the day very quickly. There was a question about does 1 over n factorial converge or diverge? Does the sum of 1 over n factorial, n goes from 1 to infinity, converge or diverge? Soon to be a new hit series, right? Converge or diverge?
Converge.
Converge. What should we compare it to? Do we want something greater than it or less than it? Greater. 1 over n factorial is less than or equal to 4 divided by, did you get this? Excellent, make sure you email me. When I look at n factorial, every term in n factorial is at least 2, except the first one, which is 1. Well, I've actually just I just protected myself by putting a 4 here. So term by term, I'm okay. This is geometric series. I multiplied by 4. That doesn't affect whether or not it converges. The sum of 1 over n factorial converges. The surprising thing is x to the n over n factorial converges for any x. And so I can change things a little bit and still be safe. Okay, so this is a good place to stop, especially since I do not know how much longer the battery